Hello class, welcome back. Today we're going to go ahead and get started on section 3.6 and 3.7, right, for module D. So for section 3.6, we are specifically going to be looking at the chain rule, right? We're specifically going to be go ahead and looking at the chain rule, right? And one way I like to go ahead and describe the chain rule is these little Russian dolls, right? So if you've ever seen these before, right? The Matryoshka dolls, it is a smaller doll inside a smaller one, right? So in other words, all of these fit inside the other one, right? So pretty much you open the big one, you end up taking out the smaller one, you open this one up, there's a smaller one in there, right? So that's how I like to think of the chain rule, and we're going to go ahead and find out how and why, right? So if you are in page 289, right, and we're looking at the chain rule, I'm going to be looking at rule, figure example 3.48 or figure 3.18, right, where it states if you're given a function, right, and right, this function that you have here with respect to x is raised to a degree like that, right? How do you take the derivative of this, right? So in other words, you can say that this is an extension of the power rule, right? The power rule that we learned in the previous section, right? So to take the derivative of this, you are going to bring down this n, right? Just like the power rule. You're going to write down exactly what you have on the inside. We know the top is going to be n minus 1. But the new part here is you're going to go ahead and multiply this times the derivative of the inside. All right, so this here is known as the chain rule, right? And some of you had asked me, hey, do I have to apply, is there going to be a time where I have to apply the quotient rule and the product rule and maybe even the chain rule? Yeah, right? So sometimes if you're doing the quotient rule, you may have to do product rule within that, all right? So, right, so this here is my chain rule, right? So let's go ahead and see an example of this, all right? What am I talking about, all right? So the first example I'm going to go ahead and look at is I'm giving you a function that looks like this, all right? That looks like this. And remember, you have to think about this, right? Because if our initial function looked like this, right, you would have to move it to make it look like that, all right? So applying the chain rule, right, I'm going to go ahead and take the derivative of this function, right? F prime is equal to, I'm going to bring that -2 to the front. This is very important, I'm going to write down exactly what is inside those parentheses. Right, on the top is going to be -2 minus 1 times, you want to go ahead and take the derivative of that. What is the derivative of 5x plus 5? Well, the derivative of 5x is just 5. And the derivative of 5, right, of this one, well, that's just a constant, right? So the derivative of that is just 0. So meaning this is what I have. All right, let me go ahead and polish this up. Right, whenever you, right, I have here 3 things that are multiplying one another. All right, generally what you want to do is move this to the front. All right, so in other words, I have -2 times 5 times 5x plus 5 to the -3, meaning the derivative of this function is just -10 of 5x plus 5 to the -3, right? And we do not want negative exponents, so my derivative is -10 over 5x plus 5 to the 3rd power. All right? That right there is the chain rule, right? That right there is the chain rule. Let's go ahead and do another example, all right? Let's go ahead and do another example. Say you have square root of squared minus 17x plus 3, right? We said in calculus, right, since we're always deriving, if we're looking at square roots, I need to go ahead and rewrite that, right? So what I have here is actually 3x squared minus 17x plus 3 raised to the 1 over 2. All right. Let's go ahead and derive this function. All right, so this means this negative a half, right? That's going to come to the front. I'm going to write down exactly what I have on the inside, right? And the reason I put a lot of emphasis on this is because the majority of the points are taken off because we take the derivative right away. All right, no. You write down exactly what you have. It is the top minus 1, right, times the derivative of this inside, right? And you may want to go ahead and pause the video, right, to find that. And you find out that the inside is 6x minus 17. All right. We know, right, focusing on that exponent up here, right, this is 1 over 2 minus 1, which is just 1 over 2 minus 1 over 1. Right, finding the LCD, that is 1 over 2 minus 2 over 2, which is negative 1 over 2. All right. So in other words, right, and this, right, I'm also going to move forward. Right, so I would probably put it like, or you may leave it back there if you want, you know. I would actually want 1 over 2 times 6x minus 17, 3x squared minus 17x plus 3 raised to the negative 1/2. All right. And we said we don't want to distribute that in there, right? It's nice how it is factored form, right? You may leave it like this, right? Or you may leave it like negative 1 over 2 6x minus 17 over 3x squared minus 17x plus 3 raised to the 1/2, right? You may leave it like that. All right. That's what I said about the beautiful thing about this class is that, all right, there's many forms, right? And we know what is to the 1/2. That is just the square root of 3x squared minus 17x plus 3. And whenever you have a fraction on the numerator, right, the numerator of the fraction stays on top and the other one stays at the bottom, right? So another way you can write this is negative 6x minus 17 over 2 square root of 3x squared minus 17x 3, right? If you are a STEM major or you're dealing with numbers, it is highly encouraged you go pretty far. Right? It is highly encouraged you go pretty far. Once you go ahead and give strength to your algebraic skills, right? Your algebraic skills, right? So that's it, right? So that's what we have here, right? That's what we have here. Let's go ahead and do our next problem, right? We have another example. All right, let's just say I'm dealing with, right, a simple one, right? Right, I have something like this. Right? I'm going to go ahead and apply chain rule, right? So this is b prime of x is equal to, so it's going to be 4 times whatever's on the inside. The degree on the top is going to be minus 1, right? And do not stop here, right? You need the derivative of the inside, right? So the derivative of the inside would be 2x minus 3 times 3 over 2x to the 3 over 2 minus 1. Right, and you may want to slow down, all right? Go ahead and take it step by step and see, right, if you have to. So here, right, looking at that exponent up there, this is 3 over 2 minus 1, which is 3 over 2 minus 1 over 1, which is 3 over 2, 2 over 2, which is 1 over 2. right? Meaning I have 4x squared minus 3x 3 over 2 to the third times 2x minus 9 over 2 x to the 1/2. All right. And specifically looking at this part, you could leave it like that, or you can use right square root of x. Right. But I would prefer if you would go ahead and revert back to the square root of x. Right. But yeah, very, very nice, right? So this here, right? That's here would be your derivative. All right, that would go ahead and be your derivative. Okay, let's go ahead and go on to a next example. Now I'm going to go ahead and do an example, but with trig functions, right? Let's go ahead and do it with trig functions, right? So we'll say I want you to take the derivative of sine of x to the 5th. Right? Be careful there, right? Because the degree is in the inside with the x, right? So how would you approach this? All right, this is the same, sort of the same method, right? So what I'm going to derive is going to be the outside part. Then I'm going to rewrite the inside as is times the derivative of the inside, right? So in other words, I'm going to go ahead and take the derivative first. This is going to be cosine of, write down exactly what you have, times the derivative of this inside, right? Which is 5x to the 4th, right? And writing this, all right, we said we want these x terms and coefficients to the front. So this is 5x to the 4th times cosine of x to the 5th. Okay. I have another one, right? What if, right? What if you had 3 cosine squared of 5x? Ooh, right? That's a lot of things going on. We said whenever we're dealing with squared, specifically if we're looking at right, trig identities, or trig functions that are squared, I want to rewrite that, right? So in other words, taking the derivative just yet, this is 3 sine of 5x to the 4th to the 2nd power. All right, and this is where I said that Russian wooden doll, the Petrushka, starts coming in, right? Because sometimes you may have to apply chain rule more than once, right? All the previous examples I had done were just one iteration. We just take chain for once. Sometimes you're going to have to dig deeper and dig deeper and dig deeper, and then you'll see, oh, okay, now I see what he was talking about that Russian doll, right? So the first thing I'm going to go ahead and do is, right, this is very different from the one we saw. This is just an extension of the power rule, right? That's going to come to the front. So that's going to give me what? 3 times 2. Let me go ahead and write everything down. 3 times 2. I'm going to write down exactly what I have. Right, on the top is going to be 2 minus 1. I'm then going to go ahead and take the derivative of the inside. All right, so let's slow it down here. Right, so the derivative of the inside, right, you're like, hey, that's another iteration of chain rule. That's fine. Right, so the derivative of the inside is negative sine. I'm going to write down exactly what was on the inside of there. Times, now the derivative of this inside, right? And the derivative of that is 20x to the 3rd. And I'm all out of Russian dolls, right? Right, so there we saw that there was a few iterations, right? So I have, since all of these are multiplying each other, I can multiply this 3 times 2 times this negative 1, right? Because there's a negative 1 here. It's just hiding, times this 20, right? So my derivative is 6 times 1 times 20, which is 120, negative 120. Go ahead and make sure. Yes, negative 120. Then going to go ahead and bring this x term, right? So this is going to be x cubed. And then I'm going to go ahead and let me go ahead and bring this one in. This is sine of 5x to the fourth times, let's go ahead and do that one, right? That's just going to be to the power of 1, so that's fine. Cosine 5x to the fourth. All right, so this is something that I would expect to give you in the exam, right? For the next for your upcoming exam, because it really puts things to the test, right? Do you really understand how to use the chain rule, right? Do you understand how to use the chain rule? So I'll go ahead and give you hints, right? In case you're not sure or you think you see it, I'll go ahead and give you hints. Hey, you got to use chain rule more than once, right? You got to use chain rule more than once. Right. One thing I wanted to mention is don't forget that on the course content, right, the list of derivatives and integrals are mentioned. We're only going to be looking at on the left column, right? We're only going to be looking at the left column. The right column would be for the second part of the class, right? But here, right, you see it's just reminders, right? The constant rule, the sum rule, the multiple power product quotient, and chain rule, right? You also have derivatives for your trigs in case you were to forget, right? So we're familiar with sine and cosine, and you're right. You see here that there's derivatives now for tangent, cotangent, secant, and cosecant, right? And just as a reminder, right, I had mentioned during lecture that whenever you're taking derivatives of trig functions that start with c's, right, it's going to change signs, right? Like cosecant, it's positive, it became negative. Cotangent was positive, it became negative, and cosine is positive, and then it turned negative, right? So it always oscillates. You have here trig identities for inverse trig functions, right? Derivatives for inverse trig functions, exponential functions, logarithms, and hyperbolic, right? So please memorize these, all right? You will not be allowed to use them during your exams. So please just know them, right? Don't memorize them, just know it, right? We don't memorize how to drive, we just know how to drive after repetition and repetition, right? Especially, right, if you're a STEM major, if you're going towards Cal 2 and in Cal 3, who knows differential equations and so forth, you really need to have these memorized. So this is the table I'm going to be referring to, right? So let's go ahead and get started with, we'll go ahead and do another example. What can I think of? Let's go ahead and do E. Function E, I'm going to be referring to for cosecant of x, right? Go ahead and move this over. I'm going to get that out of the way. All right, so well, right, another thing I wanted to go ahead and mention too, right? If you were taking the derivative of this, something like this, right, you can just focus on 4 times the derivative of just the function with the x variable, right? If you're dealing with any coefficients, you can just bring them up to the front, right? You know that whatever you have is just going to be multiplied by 4. And similarly here, right? I need to go ahead and take the derivative of this. So I already know I'm going to have a 4 in the front, right? So I need to go ahead and find out what's the derivative of cosecant of 9x, right? Cosecant, right? So first things off is I already know that it's going to be a negative something, right? Because it starts with a c, and I'm deriving it, right? And if you look at your at the list, right, as we're memorizing them, you find out that this is going to be the derivative of the negative cosecant times what you have, right, which is 9 of x. Right, that's the derivative for cosecant times, right, let's not forget, because we're still doing chain rule, right, this is times the derivative of the inside, right, which is 9, right, which is 9. Right, I'm then going to go ahead and get this 4, this 1, and this 9, meaning e prime is equal to negative 36 cosecant 9x times cotangent. Right. what is the derivative, right, for that function. All right. Let's go ahead and do another one. Okay. I'm gonna give you a list of values like, hey, f of x is this, f prime is this, g is this, and g prime is this. If I were to say, oh yeah, we started at f. That's awesome. F, right? Your function f is, let's just say g of h of x. Right. All right. Well, we will have to find. Oh, well, what is this, right? How do I derive that, right? So what we know is from the chain rule, the derivative of this is going to be g of h of x prime times the derivative of the inside. Right? And we said, right, I annotate that with a little tick that I derive that, right? All right, so this here would be the derivative, meaning I would have like a table saying g of x equals some number, g prime of x equals some number, h prime of x is equal to some number, and h prime of x is equal to some number, right? Then you would just go ahead and plug in, all right? You would go ahead and just plug in. All right, and that right there is like knowing the definition, right? That right there is knowing the definition. Okay, let's go ahead and do another one. All right, let's go ahead and do another one. All right. So now I'm saying, hey, y is equal to sine of x to the fourth minus 3, right? And so one thing I can say is find the derivative, right? I can also ask you to say find y prime, right? I can ask you find the derivative of y, but with respects to which variable? X. We need to be familiar with this, all right? So in other words, because you can have a list, all right? In other words, you can have a list, right? Because all of these are instructions. All right, and we'll say m. Right, so dy, right? So the derivative of y, how you read this is the derivative of y with respects to x. So that's just saying, hey, I want you to derive that function there, but with regards to which variable? With respects to x, meaning you're going to take things, you're going to take the derivative of anything that has an x, right? So let me erase that. So if I'm asking here, hey, find dy dx, oh, all right, I got to find the derivative of that. So, and I know that this here, all right, this here is going to be, you can write y prime, but I'm going to go ahead and write dy dx, right? The derivative of this is equal to, right? And here we got chain rule again, right? I'm going to go ahead and take the derivative of the outside, write down exactly what's on the inside times the derivative of the inside. Right, and when I polish this up, I should have 4x cubed times cosine of x to the fourth minus 3. Right. All right. Let's just say, what was it, GHI? We need this function. And I say, hey, this is 8x plus 9 to the third times negative 9x squared. We'll do minus 2 to the 9th. All right. I need you to go ahead and take the derivative of this. Whoa, right? What's going on? All right, well, what is going on? So, right, one observation you may have done already, right, is determine there are two things multiplying, right? There are two things multiplying. So, of course, what I'm going to go ahead and do is this is my f, and that is my g, right? So my f, right, my f is going to be 8x plus 9 to the third, meaning my f prime is going to be 3 8x plus 9 times 8, meaning this is 24 8x plus 9. Oh, I'm sorry, squared, right? This should be squared. My g, right, this is going to be negative 9x squared minus 2 to the 9th, meaning my g prime is going to be negative 9x squared minus 2 to the 8th times the derivative of the inside, which is negative 18x, meaning this cleaned up. Let's go ahead and see what that gives me. This is negative 162x times negative 9x squared minus 9 to the 8th, right? So at this point, I'm going to go ahead and take, now I have everything that I need to go ahead and apply, to go ahead and apply product rule, right? To go ahead and apply product rule. And in case we forgot, whenever you're multiplying two things, it is g times f prime, right? Plus f times g prime. All right, so in other words, the derivative of I to the x is equal to 9x squared minus 2 to the 9th times 24 8x plus 9 squared plus 8x plus 9 to the third times negative 162x 9x squared minus 2 to the 8th. All right, and the only thing you would have to do here is, right, is multiply your coefficients, right? Like this times this, bring it to the front. And this is that. Oh, no, this not that one. I'm sorry. This 24, bring it to the front, and that one negative 162, bring it to that front. Meaning my derivative is, I would say, 24 8x plus 9 squared times negative 9x squared minus 2 to the 9th minus 162x negative 9x squared minus 2 to the 8th times 8x plus 9 cubed. All right, I would say, hey, this right here, right, that is my final answer. All right. This here should have another parentheses right there. All right, and the one over here too. But yeah, very, very nice. Let's go ahead and do another example. All right, let's see, what can we use? It'd be nice. All right, so where did I leave off the I? So J. All right. So as a little warm up, right, as a reminder of what we're doing. All right. In case you're wondering, hey, all right, before I approach this one, hey, you say, hey, right, whenever I'm looking at this, isn't there secretly, not secretly, but behind the curtain is chain rule being applied? Yeah, it is, right? So we know that this was just, the derivative of this was just cosine of x, right? So in other words, it's the cosine of the outside times the inside times the derivative of the inside, right? What is the derivative of x? That's just 1. And anything times 1 is itself. All right, so in other words, you can say that power rule does have chain rule in it, right? It does have chain rule in it, right? Right, so the derivative of this, right, would be, that's just a coefficient, so I can just bring that down. The derivative of cosine is going to be negative sine times whatever's on the inside times the derivative of the inside, which is cosine of x. And then you can say, hey, times the derivative of the inside. Well, the derivative of that is just 1, so that's okay, right? That's okay. Meaning, all right, don't forget that this sign has all of this on the inside, all right? This sign has the term sine of x on the inside, right? So if you were to polish this up, you can have something like negative 5 sine of x times cosine x. Or you may even have right now, we'll probably write -5 cosine of x times sine of x. I usually like to leave the larger ones, the more complicated ones at the very end, right? Bring everything else a little bit forward. All right, so right, and you see that pattern, right? It's always something in the inside, right? It's always something in the inside, and that's why I was, I like referring to the I like referring to the Russian dolls. All right. It feels like that, all right, as you're extracting the derivative, right, as you're whenever you're applying chain rule more than once. All right. So, and I'll go ahead and finish 3.6 with, we already did a product with quotient rule. Let's go ahead, a product with chain rule. Let's go ahead and do a quotient rule with chain rule. Right. I was J and now I'm at L. Right. J. Oh, I'm in K. I'm sorry. Okay. Right. K of X. All right. Let's just say I have 7x plus 6 all over the square root of x squared plus 5. All right. So in other words, my top, all right, these are two things multiplying. My top is going to be f, and this is 7 plus 6. The derivative of f, that is 7. G is the square root of x squared plus 5, but I want to rewrite that, right? This is just x squared plus 5 to the 1 over 2, meaning g prime, right? If we would go ahead and do this on the side, you'd find out you get 1 over 2 x squared plus 5 to the -1/2 times 2x, right? Meaning when you clean this up, you should get x times x squared plus 5 to the -1 over 2. Right? All I did was bring 2x to the front with 1 over 2, and they canceled out. All right, so let me go ahead and apply quotient rule, right? In case we forgot, quotient rule was when you take in the derivative of something divided by something, all right? It is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. All right, all over the bottom squared. And yes, you have to simplify, right? You have to simplify, and you'll see what I mean. Meaning k prime of x is just the bottom, right, which is x squared plus 5 to the 1/2. Bottom times the derivative of the top, 7, minus the top times the derivative of the bottom, all over the bottom squared. All right, so this here ends up giving me x squared plus 5 squared. Right, and I think some of you may already see what's going on here, right? Let me go ahead and focus on the top, right, on my numerator. This is going to be polishing things up on the top. I get 7 x squared plus 5 to the 1 over 2. Right, that 1 over 2 you can convert it to the square root if you'd like. Minus x times 7x plus 6 times x squared plus 5 to the -1/2. And we know the square roots and the squared cancel each other out, meaning in the denominator, right, you just have this. In other words, this cancels out with that, right? And I would leave it like that, right? This one I would go ahead and probably leave it like that. Yeah, right. So one thing you really want to go ahead and do here to avoid getting any point deduction, right, is simplifying, right? Like specifically here in the denominator, right? You want to go ahead and cancel out those the roots and the squares, and you'll find out, right, throughout the class. It's just a thing, all right. From experience, from being a student and then teaching the class, most of the points are taken off because of algebraic little mistakes, right? I don't really like calling them mistakes, but just mishaps, all right? Most of the points are taken off because of algebraic stuff, and it's not because of the calculus part, right? It's crazy how the majority of the points are taken off because of algebraic reasons, not, right, for the most part, not calculus reasons. Right, and if you notice, this is just this is something you just got to do a lot of, right? This is something you got to do a lot of to get the rhythm of it, right? To get the rhythm of it. So this here concludes 3.6. All right, we're going to go ahead and go to 3.7. All right, I'm going to go ahead and want to go to 3.7. All right, we're here. We're going to go ahead and get started with some inverse trig functions, right? So specifically, right, you want to go ahead and look at your list. All right. All right, for this section, we're going to be focused on this part here, right? On this part here, the inverse trig functions, right? Right. So, and with inverse trig, right, with these inverse trigs, right, there's still going to be, right, there's going to be still a chain rule or quotient rule or power rule or product rule implied into each one of them. All right. So we'll go ahead and look at the first one. All right. So I say, hey, you're giving this function. All right. You're giving inverse sine of -1 x. All right. The derivative of this, all right, is going to be 1 over, right, and listen to these words, right, what I'm saying here, 1 over the square root of 1 minus whatever is on the inside squared. So it's not always going to be x squared, it's everything that is on the inside of sine squared, right? That times the derivative of the inside, right? So in other words, with this one, you may even have to apply chain rule, right? Well, this is going to be times 1, so this is how it looks like, right? This is how it looks like. This is how it looks like. All right, and you know what? Let me color code something here. All right, let me go ahead and write this x in green and that x in green to remember to go ahead and so you can go ahead and not forget, all right, to go that it's everything on the inside. It's not just x. So let's get started, all right. And I'm only going to be doing a few of these, right? In other words, I'm going to be doing a few sines and a few cosines, but right, the same idea would follow. It's just the formula that changes, right? So if you're doing inverse tangent of x, right, it's whatever's on the inside, that x, that's going to go inside that x value there, all right, and so forth. So it's not only x, it's just whatever's on the inside of that trig function. All right, so I'll go ahead and stop talking and get started. I think we left off in L. Right, so L of x is equal to, I'm asking you to find the derivative of inverse sine of 3x. Right, okay, so following the formula there, right, this is L prime is going to be 1 over the square root of 1 minus everything on the inside, right? So as a force of habit, what I would go ahead and do is just make sure you put in parentheses and then squared, right? Everything in the inside. And remember, we're not stopping here yet. Times, right, we're still applying chain rule. Times the derivative of the inside. The derivative of this is going to be 3. All right? Meaning, when I clean this up, 1 times 3 in my numerator, this gives me 3 over the square root of 1 minus 3x squared, right? 3x squared, this is just 3 squared times x squared, which is 9x squared, right? So in other words, this is 9x squared. And this, ladies and gentlemen, is your final answer. Right? It's still pretty straightforward, right? Nothing too difficult. We're still doing, right? We're still applying the rules that we know, right? So what I like to tell students is, hey, one thing I do not want you to do is just, hey, I studied for this exam, I'm going to go ahead and clear my recycling bin and erase everything. No, right? It all builds upon each other. These are all tools. You're like Batman and Batgirl and Batwoman, right? And Robin. You have this utility belt with all these tools, and through our class, we're going to be using these tools, right, to solve problems. All right, that's what we're going to be doing. So please be sure that you print out the list of derivatives and integrals, right? Because those are key. All right, it's important. Right, and you probably know by now, right? Make sure you write whenever you're doing your homework. Write down notes, right? Keep things handy, all right? whenever you have to go back and look at to see what you did, right? Okay, I'll stop and I'll go ahead and get started on another one. All right, let's just say, what was it? LM. Right. Let's say I want you to find the derivative of inverse tangent, right? Since it just did that one, 3x to the 4th. Right, and if we look at inverse tangent, right, the derivative of inverse tangent is here. 1 over 1 plus x squared. All right, or in other words, 1 over 1 plus whatever is on the inside squared times the derivative of the inside. All right, times the derivative of the inside. So let me go ahead and just write this out. All right, so then this here, it's just going to be, I know m prime is just going to be 1 over, right, 1 plus whatever's on the inside squared times the derivative of the inside, all right? So the derivative of this, you'd see this gives me 12x to the 3rd. I'm going to go ahead and polish this up. And yes, for these, you do have to simplify, right? Leaving it just like this will not be acceptable, right? Because, all right, these are little things you know how to simplify, right? You know how to take the second power to the values on the inside, and you know how to multiply 1 times 12x cubed, right? So this is just 12x cubed over 1 plus 9x to the 8th, all right? Whenever you have, in case you're wondering, whenever you have a degree raised to another degree, right? They cancel each other out. No, don't cancel them out. They multiply each other out, right? So this here is the derivative, right, of inverse tangent 3x to the 4th. Right. Let's go ahead and do another one here. All right, so let's just say you had, go ahead and have some fun with these, right? Let's see here. Let me go ahead and pull one up. Okay, here's a fun one, all right? I have 7 tangent of 2 sine of 4x. Right, step at a time, right? Step at a time. If you notice, right, right, if you're feeling discouraged, because be like, hey, right, because one thing I used to do as a student, I used to look at the back of the book, right? I used to look at the solutions and be like, all right, I'm gonna check if my work matches, right? If it is yes, I feel confident. If it's not, then it would bother me because I felt like I was solving it the wrong way, which is the opposite of what I want to do, right? And with this class, I started realizing that, hey, my answer does not look like nothing like what was in the back of the book or in the solutions manual, right? And it didn't show you the steps, right? It would just give you the answer, and so it would discourage me, right? And so what I started doing was just asking my professor, right? Going to his office, I would be like, hey, can you just check this real quick, or ask my classmates, right? So that's what I recommend you do. If you solve something and you're just not unsure, let me know, and I'll go ahead and send me you would send me a picture of your work, and I'll go ahead and scan it real quick and be like, all right, and see if I can find a location, if there is an error. If not, then it's great, you're solving it correctly. So please go ahead and do that. You may share it on you may share your work and stuff with me via email and stuff, and to let me know. Okay, I'll go ahead and stop and let's get started, right? So we are looking for n prime of x at a time, right? That is just a coefficient. So this is 7 times, I'm going to take the derivative of inverse tangent, right? So in other words, the derivative of inverse tangent is 1 over 1 plus whatever's in the inside squared. All right, so I'm going to get whatever is in the inside of tangent and just square it. All right, looks kind of odd, but that's okay. Squared times the derivative of this inside, right? And if it helps you, right, if it helps you, like, you know what, let me go ahead and write this on the side so I can see it, right, and not get lost in what's going on, then go ahead and do that. That's totally fine. right? You find out that this derivative here, right, is, if we would go ahead and complete this out, this would give you 8 cosine of 4x. Right, so that is the derivative. So in other words, you would multiply this, all right, by 8 cosine of x. All right, go ahead and multiply that by 8 cosine of 4x. All right, and of course, like I said, right, we got to simplify this, right? I got 7 times 8, all right? I have that on the top. 7 times 1 times 8, right? That's just going to give me, what, 56 cosine of 4x. And of course, I need to simplify that squared, right? So this is going to be 1 plus 4 sine squared of 4x, right? And that's what I have. And that's what I have. So, and like I said, right, you may have to do product rule with these, right? You may have to do quotient rule with these. It's all fair game, right? Now I would, like I said, one thing you may want to do is whenever you're doing product and quotient is just write everything out, or write everything out. Right, because it's better safe than sorry, right? At least you're able to visualize to see where you may have gone off, right? When you may have gone wrong. Okay, and these are only ones I have for you all today, right, in terms of computational ones, right, in terms of computational ones. But there are 2 word problems I wanted to go ahead and get started on, because exam 2 and 3 are going to be pretty word problem heavy, right? And I figured I'm going to go ahead and add 2, right, to this section 2. Let's go ahead and get started, all right? So you're told here that a pole stands 75 feet tall at this given angle, right, at that given angle. It's formed when wires of various length of x are attached from the ground to the top of the pole. All right. They want you to go ahead and find the rate of change of the angle when a wire of 250 feet is attached. All right. So I need to go ahead and set up a trig identity that uses theta, and it uses this and this. Right. And let's go ahead and do a little blast from the past, right? And I'm going to go ahead and do SOHCAHTOA, right? SOHCAHTOA, right? Where sine is opposite over hypotenuse, right? Cosine is adjacent over hypotenuse, and tangent, right, is opposite over adjacent, right? So in other words, if this here is my takeoff angle, right, the hypotenuse is the slant, the one on the other end is my opposite. What I have here on the flat ground would be my adjacent. I'm looking for something that uses opposite on a hypotenuse, and we determine that that is sine, right? I'll go ahead and determine that is sine. So in other words, that is exactly what I'm going to want to use. I'm going to want to go ahead and start off with that, all right? I'm going to want to go ahead and set up this identity. So in other words, I have sine of theta is equal to 75 over x. All right, and this section is right. This section and the previous sections are very, very important. All right, and we'll go ahead and see why. Since I'm finding d theta over dx, all right, one thing that I may want to go ahead and do here is go ahead and move this over real quick. Go ahead and move this over real quick. There. Okay. What I'm going to go ahead and do here is derive the left-hand side. All right. I'm going to go ahead and derive the left-hand side. So on the left-hand side, whenever I derive this with respects to theta, all right, I get theta. All right. Is equal to, I'm going to go ahead and now derive the right-hand side, right? I'm going to go ahead and derive the right-hand side, but with respects to x, all right? And right, I said that this is the same thing as this, and the shortcut would have been something like that, right? Another thing you could go ahead and do is move, you know that 75 over x is the same thing as 75 times x to the -1. Right, you can go ahead and apply the power rule, and you'd find out that you end up getting negative 75 over x squared. All right. This was I think from a section or two behind. All right. So hey, I went ahead and already I derived both of these, right? I went ahead and derived the first one with respect to theta. I went ahead and derived the second one with respect to x. All right. What I'm going to go ahead and do now is I'm going to go ahead and let's see here. What can I do? Actually, I'm sorry. Let's go ahead and backtrack, right? Because I realized I was doing something else. All right. Let's go ahead and go up to here. All right. Since then, obviously where my train of thought ran off. Right. Since I'm trying to find this, right? Since I'm trying to find this, we said in the previous problem, right, that if I had something like this, right, this is telling me which function to derive, and the bottom is telling me which with respects to which function. All right. So in other words, I want to go ahead and get theta by itself. All right. I want to go ahead and get theta by itself. Meaning, if we remember from trig, how do you write? If you have a term on the inside that's locked in because of sine, what are you going to do? You're going to go ahead and take the inverse sine to both sides, right? Or arc sine to both sides, right? Meaning, why do I want to do that? Because these two would cancel out, leaving me with theta is equal to inverse sine of 75 over x. And at this point, right, I can go ahead and I know how to take the derivative of this, right? I know how to take the derivative of this. This is going to be the derivative of theta with respect to x is equal to, right, we said the derivative of inverse sine was 1 over the square root of, let's see here, 1 minus everything on the inside, squared times the derivative of the inside. All right. And if you notice, right, that's exactly, I had jumped ahead. The derivative of 75 over x, right, we determined that this is negative 75 over x squared. All right. Negative 75 over x squared. All right, let me go ahead and clean this up. So I get d theta over dx is equal to 1 over square root of 1 minus 75 squared over x squared times negative 75 over x squared, right? Now that you've gone ahead and taken the derivative, right? Once and only once you have taken the derivative, you want to go ahead and plug this in for your x value, right? The given, your 250 feet, right? So you would go ahead and do is plug in 250, right? For let x equals 250, go ahead and plug this in, and the value there is going to be your answer, all right? Be sure that you round your answer to 5 decimal places, right? To 5 decimal places. So yeah, all right, I'll go ahead and let you solve this one for yourself, right? If you want to go ahead and get the answers to this one, right? If you were working here, right, you find out that the answer you end up getting here, all right, because this is algebraic, I have confidence in all of you, all right? This is negative 0.00126. Oh, that looks like cherries, but it's supposed to be zeros, right? This here would go ahead and be your value, right? Let's go ahead and do another one. Let's go ahead and do the word problem number 2, right? Word problem number 2. Something similarly, right? A TV camera at ground level is 2,000 feet away from the launching pad of a space rocket, right? That is set to take off vertically, as seen in the following figure. The angle of elevation of the camera can be found by, all right, they've already gone ahead and solved theta for us, all right? Using SOHCAHTOA, you could have told that this is tangent of theta. What's given is adjacent and opposite, which is tangent, right? That's how I know to use tangent equals x over 2,000. And it took the step of solving for theta by itself, like we did in a previous problem, giving us theta, right, is equal to inverse tangent of x over 2,000. right, where x is the height of the rocket. Find the rate of change of the angle of the elevation when the camera and the rocket are 5, 7, 9, 8. Right, so very similar to what we were doing earlier, right? So what I'm going to go ahead and do here, right, is going to be find d theta over dx, right, inverse tangent, right, and with inverse tangent, right, it is 1 over 1 plus whatever's on the inside squared, right, whatever's on the inside is x over 2000, right, times the derivative of the inside, right, right. So whenever you have x over 3, this is the same thing as 1 over 3x, right? And the derivative of a variable that just has the 1 is just the coefficient in front of it, right? That meaning that if you were looking at x over 2000, this is technically 1 over 2000 times x, which is just, right, that's a term of degree 1, right? X to the 1. And I know that the derivative of that, pretty much the x just disappears, leaving me with just the coefficient. Meaning this is 1 over 2000. Right, so that right there would be my derivative of that. So let me go ahead and polish that up a little bit more, leaving me with d theta dx is equal to 1 over 1 plus x squared over 2000 squared times 1 over 2000. All right, and just go ahead and be careful, right? If you want to go ahead and unify these before you go ahead and plug in your x values, right? Your x value here would be 5798. On the top is 1 times 1. This is 1 over parentheses, right? Because this is going to have to multiply to both of them. Right? I would probably just leave it like times 2000. And then I would go ahead and plug it in. Oh, you know, whatever helps, right? You could have plugged in x right here right off the back, or you could have gone ahead and applied it there or here. All right. But yeah, that is it, right? I'll go ahead and let you solve that one out, right? Whenever you would go ahead and plug in, right? Maybe you would go ahead and plug into 5 decimal places, right? All right, you would find out that this here gives you 0.00001, right? That would go ahead and be your answer. If you want to go ahead and give more, that's completely fine, right? But yes, that is all I have for you all today. Thank you very much for your time, and I hope you enjoy the rest of your day. Thank you.